In our last lecture, we have seen that in some cases, there will be no uniformly minimum variance unbiased estimator for a given parametric function. In the present lecture, we shall prove that if there exists a uniformly minimum variance unbiased estimator, then it will be unique. We shall also derive some properties of a uniformly minimum variance unbiased estimator by using the method of covariance. We shall introduce the idea of efficiency of an unbiased estimator. We also provide a bound for the correlation coefficient between the two unbiased estimators of a parametric function based on their efficiencies. In the present module, we shall discuss some results relating to a uniformly minimum variance unbiased estimator. Result 1. A uniformly minimum variance unbiased estimator, if exists, is unique. Proof. If possible, suppose T1 and T2 be two UMVUEs of g theta, then expectation of T1 is equals to expectation of T2 and variance of T1 is equals to variance of T2 for all theta. Define a statistic capital T such that T equals to half into T1 plus T2. Then expectation of T equals to half into expectation of T1 plus expectation of T2, which is equals to g theta for all theta, and variance of T is equals to 1 by 4 into variance of T1 plus variance of T2 plus 2 covariance T1, T2. If rho theta T1, T2 be the correlation coefficient between T1 and T2, then covariance T1, T2 is equals to rho theta T1, T2 into root over variance of T1 into variance of T2, which is equals to rho theta T1, T2 into variance of T1, because variance of T1 equals to variance of T2. Hence, we get variance of T is equals to half into variance of T1 into 1 plus rho theta T1, T2. Since T1 is a UMVUE of g theta, variance of T1 is less than equals to variance of T for all theta, which implies that rho theta T1, T2 is greater than equals to 1 for all theta. Since rho theta T1, T2 cannot be greater than 1, it follows that rho theta T1, T2 is equals to 1 for all theta, which implies that T1 and T2 are exactly linearly related. That is, probability T1 equals to sum A theta plus B theta into T2. This is equals to 1 for all theta, where A theta and B theta are constants, which implies that expectation of T1 is equals to A theta plus B theta into expectation of T2 for all theta, which again implies that g theta equals to A theta plus B theta into G theta for all theta, which is an identity in theta. Comparing the coefficients, we get A theta equals to 0 and B theta equals to 1 for all theta. Hence, T1 equals to T2 with probability 1 for all theta. Next, we consider the second result. Result 2. The correlation coefficient between the UMVUE and any other unbiased estimator of G theta is always non-negative. Proof. Let capital T be the UMVUE of G theta and T dash be any other unbiased estimator of G theta. Then expectation of T is equals to expectation of T dash is equals to G theta for all theta. Let us define a statistic H equals to T minus T dash. Then expectation of H is equals to 0 for all theta. Hence, H is an unbiased estimator of 0. By the method of covariance, covariance T, H is equals to 0 for all theta, which implies covariance between T and T minus T dash is equals to 0 for all theta, which implies covariance T, T dash is equals to variance of T for all theta. The correlation coefficient between T and T dash is given by rho theta equals to covariance under theta T, T dash whole divided by within square root variance of T into variance of T dash. Since covariance T, T dash is equals to variance of T, we get rho theta equals to within square root variance of T divided by variance of T dash for all theta, which is always non-negative. Note: the efficiency of T dash with respect to T is defined by E theta equals to variance of T divided by variance of T dash for all theta. From the above result, we get rho theta equals to root over E theta for all theta. Next, we consider result 3. If T1, T2 up to Tk are the UMVUEs of G I theta for all I from 1 to k, then summation over I from 1 to k ai into ti is the UMVUE of summation over I from 1 to k ai into G I theta, where a1, a2, ak are real constants. To prove the result, note that expectation of Ti equals to Gi theta for all I. Hence, expectation summation over I from 1 to k ai into Ti is equals to summation over I from 1 to k ai into Gi theta for all theta. Hence, summation over I from 1 to k ai into Ti is an unbiased estimator of summation over I from 1 to k ai into Gi theta. Since Ti is the UMVUE of Gi theta for all I, by the method of covariance, expectation under theta Ti into H is equals to 0 for all theta and for all H belongs to U naught. which implies expectation under theta summation over I from 1 to k ai into ti into h is equals to 0 for all theta and for all h belongs to u naught. Hence, summation over I from 1 to k aiti is uncorrelated with every unbiased estimator of 0, and hence by the method of covariance summation I from 1 to k ai into ti is the UMVUE of summation I from 1 to k ai into gi theta. Next, we consider result 4. If T1, T2 up to Tk are the UMVUEs of gi theta I from 1 to k, then product over I from 1 to k Ti is the UMVUE of its expectation. Proof. Let H belongs to U naught. Since T1 is the UMVUE of G1 theta, by the method of covariance, expectation under theta T1 into H is equals to 0 for all theta, which implies T1 into H is an unbiased estimator of 0, that is, T1 into H belongs to U naught. Again, T2 is the UMVUE of G2 theta. We get expectation under theta T2 into T1 into H is equals to 0 for all theta, which implies T2 into T1 into H belongs to U0. By a similar argument as before, we get expectation under theta T3 into T2 into T1 into H is equals to 0 for all theta. Proceeding in this way, we finally get expectation under theta product over I from 1 to k Ti into H is equals to 0 for all theta. Hence, product over I from 1 to k Ti is uncorrelated with every unbiased estimator of 0, and hence product over I from 1 to k Ti is the UMVUE of its expectation. Note that if T is the UMVUE of g theta, then by the above result, T to the power k is the UMVUE of its expectation, where k is any positive integer. Next, we consider result 5. If the sample consists of n independent observations from the same distribution, then the UMVUEs are symmetric in the observations. Let us consider a proof of this result. Let x1, x2 up to xn be a random sample of size n drawn from a population with probability function f theta x, where theta is an unknown parameter. Suppose T x1, x2 up to xn be an unbiased estimator of g theta with variance of T is equals to sigma square. Let us consider a symmetric function of x1, x2 up to xn, namely T star equals to 1 by n factorial into summation T xi1, xi2 up to xin, where the summation being taken over all possible permutations of I1, I2 up to In of 1, 2 up to n. then expectation of T star equal to G theta, and variance of T star is equals to 1 by n factorial square summation variance T xi1 xi2 up to xin plus 1 by n factorial square into summation covariance T xi1 xi2 xin and T xj1 xj2 up to xjn. We write this as equation 1. Now, by symmetry, variance T xi1 xi2 up to xin is equals to sigma square for all theta. For any permutations of I1, I2, In. Also, by Cauchy-Schwarz inequality, covariance T xi1 xi2 up to xin and T xj1 xj2 up to xjn is less than equals to sigma square for all theta. For any two different permutations I1, I2, In and j1, j2 up to jn. Hence, from equation 1 we get variance of T star is less than equals to sigma square into n factorial plus n factorial into n factorial minus 1 whole divided by n factorial square, which is equals to sigma square for all theta. Hence, T star is the UMVUE of G theta. Next, we consider another result. Let T1 and T2 be two unbiased estimators of G theta with efficiencies E1 and E2 respectively. Then modulus rho minus within root over E1 into E2 is less than equals to within root over 1 minus E1 into 1 minus E2, where rho is the correlation coefficient between T1 and T2. Let us consider a proof of this result. Let T be the UMVUE of G theta with variance of T is equals to sigma square. Then variance of Ti is equals to sigma square by Ei for all I equals to 1, 2. Let us define a statistic T star such that T star equals to alpha into T1 plus 1 minus alpha into T2 for any constant alpha belonging to the interval 0, 1. Then expectation of T star is equals to alpha into G theta plus 1 minus alpha into G theta, which is equals to G theta for all theta, and hence T star is also an unbiased estimator of G theta. Now, variance of T star is equals to alpha square into variance of T1 plus 1 minus alpha whole square into variance of T2 plus 2 into alpha into 1 minus alpha into covariance between T1 and T2, which is equals to sigma square into alpha square by E1 plus 1 minus alpha whole square by E2 plus 2 alpha into 1 minus alpha into rho into within root over 1 by E1 into 1 by E2. Since T is the UMVUE of G theta, variance of T is less than equals to variance of T star for all theta, which implies alpha square by E1 plus 1 minus alpha whole square by E2 plus 2 into alpha into 1 minus alpha into rho into within root over 1 by E1 into 1 by E2 is greater than equals to 1. After some routine algebra, we get a into alpha square plus b into alpha plus c greater than equals to 0. We write this as equation 1, where a equals to 1 by E1 plus 1 by E2 minus 2 into rho divided by within root over E1 into E2. B equals to 2 into rho divided by within root over E1 into E2 minus 1 by E2, and C is equals to 1 by E2 minus 1. From equation 1, it is clear that the discriminant of the quadratic equation a alpha square plus b alpha plus c equals to 0 cannot be positive. Hence, we get rho divided by root over E1 into E2 minus 1 by E2 whole square is less than equals to 1 by E1 plus 1 by E2 minus 2 into rho divided by within square root E1 into E2 into 1 by E2 minus 1, which implies rho divided by root over E1 into E2 minus 1 whole square is less than equals to 1 minus 1 by E1 into 1 minus 1 by E2, which implies within modulus rho minus root over E1 into E2 is less than equals to within root over 1 minus E1 into 1 minus E2. Note that if T be the UMVUE and T dash be any other estimator of G theta with efficiency E, then from the above result we get 1 minus 2 into E is less than equals to rho less than equals to 1, where rho is the correlation coefficient between T and T dash. In the present lecture, we have seen that if a UMVUE exists, then it must be unique. The correlation coefficient between the UMVUE and any unbiased estimator must be non-negative. If T1, T2 up to Tk are the UMVUEs of G1, G2 up to Gk, then summation over I from 1 to k ai into Ti and product over I from 1 to k Ti are the UMVUEs of their expectations. If a sample contains n independent observations from a given population, then the UMVUEs are symmetric in the observations.